Swayam Prabha, free DTH channel for education.
Okay. Next one, what we are going to discuss is we are going to discuss about the Frobenius method. In Frobenius method, what we are going to deal is that we are going to deal with the different kinds of solutions which we are going to find. Okay, for that we need to, for Frobenius method, first we need to understand some of the basic idea of this, some more basic idea about this power series. So what we are going to see is that we are going to have a things called analytic. Okay, what is analytic we will discuss, and then we'll go to some of the things like regular singular point and irregular singular points. In tomorrow's class, we'll discuss about what is the Frobenius method, etc. Okay, so we say, so you remember this one. So initially I have written summation m equal to 0 to infinity am into x minus x naught power m. I have written that in as f of x. Okay, if it is convergent, I have written as f of x. So we say that suppose a function is given, okay, suppose some function is given, suppose f is a function given, okay, if it's a function from, let's say, r to r is given, okay, so we say that f is analytic at a point x naught, okay, f is a function from r to r is given, okay, then I say f is analytic at a point x naught. When do I say x naught? If I can write this as, okay, if I can write this as f of x equal to summation m equal to 0 to infinity am into x minus x naught power m in the small interval of convergence, small positive radius of convergence, where this is defined. Means I need to have some x minus x naught, okay, less than r. This r should be positive. Okay, so it means like we have at least some positive radius of convergence or infinite radius of convergence. Yeah. So in that case, we say that this f is analytic. Okay, the function f is said to be analytic at that point. Okay, only at x naught only I am going to say. Now, if it is analytic at all the points, if it is analytic at all points in this real line, then we say that the function is analytic. Okay, so first I am defining if it is analytic at a point, then I am extending if it is defined for all, if it is analytic at all points, then I say that it is analytic. Okay, so here x is a variable. Here x is a variable, and a0, a1, a2 are constant as we discussed in the earlier case, and x0 is called the center of the power series, center of the series. Now what I have, suppose I have given a problem. Okay, y double dash plus p of x into y dash plus q of x into y is given. So this is the problem we were solving in the previous classes. Okay, so this problem is given to you, or equal to r of x also you can take. Okay, so you can take equal to r of x also. Now we say that this function, okay, this we say, now suppose you consider a point. For example, this x naught is there, right? Now consider a point x naught. Okay, we say that this x naught is ordinary point. Okay, we say that this x naught is ordinary point. When do we say it is an ordinary point? Okay, if this coefficient p of x, okay, is analytic, p of x is analytic, and q of x is analytic. Okay, if p of x and q of x are analytic, then we say that it is a ordinary point. Means what is the meaning? So it is, you should have a positive radius of convergence in such a way that p of x equal to summation m equal to 0 to infinity am into x minus x naught whole power m should exist. Okay, similarly q of x equal to summation m equal to 0 to infinity, let's say some bm into x minus x naught power m should exist for some positive radius of convergence. So in that case, we say that p of x and q of x are analytic. Okay, so in that case, this x naught is said to be an ordinary point of this problem, okay, of this ODE. If x naught is not an ordinary point, okay, I have a point x naught, okay, I have a point x naught. If it is an ordinary point, I say it is an ordinary point. Okay, ordinary point means p of x, q of x, analytic. Okay, singular point. If it is a single, then otherwise I call it a singular point. That is, what is the meaning? Either p of x or q of x is not analytic. Okay, either p of x or q of x is not analytic. If one of them are not analytic, we say that it's a singular point. Okay. Now again, the singular point also I will classify further. Okay, how do I classify? So that we will see it. Okay, the next slide. So suppose your P of x and Q of x are analytic at x equal to 0, means x naught is an ordinary point. Then what this theorem, existence of power series solution, this theorem is going to say is that the solution of this problem, the solution of this homogeneous problem, let's say, okay, the solution of this problem is going to exist. Okay, every solution of this one is analytic. Okay, what it is saying, it is going to be analytic. Every solution of this problem is going to be analytic. Y is going to be every solution is going to be analytic. Okay, every solution of this problem is going to be analytic at x equal to 2. Okay, and that can also represented in that way. So since it is analytic, you can write that y of x equal to, you can write this as, you can write a similar way, summation, some, let's say m equal to 0 to infinity, some cm into x minus x naught whole power m is going to exist. Okay, that's what we say it is a analytic, and that is also a positive radius of convergence. Okay. Now again, if it is a single point, I can classify this further. Okay, if a single point, I am going to classify this further. What I am going to do is that I am going to classify this as regular singular point, okay, and irregular singular point. So what is a regular singular point means? What I am going to do, I am just going, since P of x and Q of x are not analytic, okay, both are not, either one of them is not analytic. So in that case, I am going to define x minus x naught into P of x. Okay, I am going to check whether this is analytic. Okay. Then second thing I am going to check x minus x naught whole square into Q of x, whether this is going to be analytic. If these two are analytic, then I say that singular point is called the regular singular point. Okay. If one of them is not there, okay, either x minus x naught is not P of x is not analytic, or x minus x naught whole square P of x is not analytic. Okay, or this one. If one of them is not analytic, then we say that singular point is called the irregular singular point. Okay, the point is said to be regular if x minus x naught into P of x plus in then x minus x naught square into Q of x will be analytic. Then we say that it is a regular singular point. Otherwise, it's called as a irregular singular point. So, for example, you can see this problem. You can identify what are the regular and irregular singular points. Okay, let us see this problem. So, x minus x naught x square minus 4 whole square. Okay. So, I have the problem like this: x square minus 4 whole square, x square minus 4 whole square into y double dash, okay, plus 3 into x minus 2 into y dash plus 5y equal to 2. Let us see whether it is regular or ordinary point. What are the ordinary point or regular singular point? So, what is my P of x here? So, P of x is nothing but 3 into x minus 2 divided by x square minus 4 whole square. Okay. So therefore, this is going to become like, I can write it as 3 into x minus 2 into this one, I can write it as x minus 2 whole square into x plus 2 whole square. I can write it. Okay. So therefore, this is going to become like this one gets cancelled. Therefore, I'm going to 3 by x minus 2 into x plus 2 is going to come. Okay. X plus 2 whole square is there. X plus 2 whole square is going to come. So in this case, you can see whether what is the where it is going to be defined, etc. If I put x equal to 2, okay, if I approaching x equal to 2, then this is going to become like infinite. Therefore, at 2, it is not defined. Similarly, if I put minus 2, again this is going to become like 0. In the denominator, it is going to become 0. Therefore, minus 2 is also not a regular singular point. So, except 2 and so at 2 and minus 2, okay, at 2 and minus 2, except, okay, let us write it except 2 and minus 2, okay, except 2 and minus 2, P of x is analytic. Okay, analytic. Now Q of x let us consider. So except this one is analytic. Now Q of x is nothing but 5 by x square minus 4 whole square. Okay, so that is going to become like 5 by x minus 2 whole square into x plus 2 whole square. Once again, at x equal to this is going to become like infinite. This is going to be x equal to minus, this is going to be infinite. Therefore, except 2 and minus 2, okay, Q of x is also analytic. Therefore, what you can say, except 2 and minus 2, okay, except 2 and minus 2, except 2 and minus 2, rest are ordinary points. Okay, rest are ordinary points. Or I can write So I have the point. Okay. I have a point in R. Okay. So ordinary points R minus 2 comma minus 2. Okay. Singular point is nothing but minus 2 comma 2. So this is the ordinary point. This is singular point. Okay. Now we got to check whether this is a regular or irregular singular point. Okay. Whether minus 2 and 2, whether they are regular or irregular, we got to check. So if I put minus 2 here. Okay. So suppose for that what I need to check, I got to check x minus x naught into p of x. I got to check. So now let us consider x minus 2 into p of x. Okay. So that is going to become like 3 into x minus 2 is going to come. X minus 2 gets cancelled. Therefore, you are going to get 3 by x plus 2 whole square is going to come. Therefore, at this place, except I'm just substituting minus 2. So except that everything is fine for me. Okay, but at x equal to 2 only I have to check whether this is going to be. So it is going to be defined. Okay, therefore this is analytic. At x equal to 2, this is analytic. Okay, now x minus 2 whole square. X minus 2 whole square into p of x, q of x. X minus 2 whole square into q of x. So that x minus 2 whole square will get cancelled. So you are going to get 5 by x plus 2 whole square is going to come. Therefore, this is analytic again. Okay. Since this is okay. So therefore, at x equal to 2, both are analytic. Therefore, what I can do, I can write this as under regular singular point. Okay. So 2 x equal to 2, if I put that is going to become like regular singular point. Now for x equal to minus 2, I got to check. So in that case, I got to check x plus 2 into p of x. I got to check. Okay. That is going to become like 3 by x minus 2 into x plus 2, because only one x plus 2 will get cancelled. So still if I substitute x equal to minus 2, this is going to become like not defined. Therefore this is going to become like minus 2 is going to become like irregular singular point. Okay, irregular singular point. So minus 2 is regular singular point, minus 2 is not at x equal to minus 2. P of x is not analytic, therefore you can immediately say that it is going to be like not an irregular singular point. Okay. In fact, I can verify x plus 2 whole square into q of x is analytic, but at least one is not analytic, then you can say that this is not going to be regular singular point. Okay. Same y double dash plus 4x square y dash plus 3y equal to 0 is there. Okay. So let us check whether this is again regular or irregular or ordinary point. Let me find it out. So p of x is going to become like 4 by x. Q of x is going to become like 3 by x square. 3 by x cube actually. Okay, 3 by x cube. So in this case, once again, you can check that x equal to 0 is the only place where p of x is not defined and q of x is not defined. So for r, okay, for r, if you define like r minus 0, except r minus 0. So r minus 0 is ordinary point, 0 is singular point. Okay, 0 is singular point. Now we got to check whether it is irregular or regular. So if I just substitute x into p of x, okay, x into p of x is going to become like 4, no issues. Okay, whereas x square into p of x is going to become q of x. Okay, x square into q of x is going to become like 3 by x. Where once again it is not defined at x equal to 0. Therefore, 0 is irregular singular point. Okay, so there is no regular singular point is there, only irregular singular point is there. So next problem. So in this problem we have 3xy double dash plus y dash minus y equal to 0. Okay, so let us see this problem. Here p of x is going to be 1 by 3x and q of x is going to be minus 1 by 3x. Okay, so let us see what is going to happen here. Once again, at x equal to 0, I can see that x equal to 0 is singular point. Okay, so I can define once again same thing. So if I put r, so this is going to become like ordinary point. Ordinary point is r minus 0. Okay, except that, and singular point is going to be 0. Okay, now we got to check whether it is regular or irregular. So x into p of x is going to become like 1 by 3, and x square into q of x is going to become like minus x by 3. So both are defined. Therefore, this is going to become like regular singular point. So there is so regular singular point is 0. There is no irregular singular point. Okay. Next problem. For one more problem. So next problem is x square plus x minus 6 into y double dash plus x plus 3 into y dash plus x minus 2 into y equal to 0 is there. So in this case, p of x is going to become like x plus 3, okay, divided by, I can write it as x square plus x minus 6, I can write it as, so x square plus x minus 6 in factor it, okay. So this is going to become like x plus x minus 2, okay, x minus 2 into x plus 3, I can write it, okay. So 3 minus 2, 6, 3 plus x, okay. So I can write it as x plus 3, okay, I can write it as x minus 2 into x plus 3, okay, and q of x is going to become like x minus 2 divided by x minus 2 into x plus 3 is going to come. So this is going to be simply 1 by x minus 2 and this is going to be simply 1 by x plus 3. Okay, so therefore you can see that at x equal to 2, p of x is not defined, therefore it is not analytic at x equal to 2. At x equal to minus 3, q of x is not defined, therefore you can say that this is not going to be analytic at that case. So therefore in that case, your r, you will put r, so g ordinary points, so the ordinary points are going to become like r minus 2 comma minus 3 is going to be, okay, whereas 2 and minus 3 they are singular points, okay, this is singular point. Now you got to check which is regular and which is irregular. So in that case, if I substitute, first let us calculate this one, x minus 2 into p of x, okay, x minus 2 into p of x, therefore this is going to get cancelled, that is going to be like 1, and x minus 2 into q of x minus 2 whole square into q of x, so that is going to become like x minus 2 whole square into divided by x plus 3. So there is no issues over here. Therefore, this is going to be regular singular point. Okay. So 2 is going to be regular singular point. Now x minus 3 into x plus 3 into p of x is going to become like 1 x plus 3 by x minus 2. Okay. And x plus 3 whole square into q of x is going to become like x plus 3 divided by x plus 3, that's all. Okay, so this is again going to be analytic, this is going to be analytic at x equal to 3, therefore x equal to minus 3 is also regular singular. So both are regular singular points. Okay, now next one what we are going to discuss is that we are going to discuss the Frobenius method. So in Frobenius method, what I am going to do is that I am going to take the problem of this kind, again the same kind of similar kind of problem only we are going to take. So what we will is what we are going to do is that we are going to take this problem, y double dash plus p of x divided by x plus c of x divided by x square into y, here y dash equal to 0. Let us consider this problem. Okay, so now p of x and c of x are analytic. So let us assume that p of x and c of x are analytic at x equal to 0. Okay, then the ODE, this ODE has at least one solution, and that solution is of this form, y of x equal to, okay, this solution is going to be of this form, y of x equal to x power r into summation m equal to 0 to infinity am into x power m is going to be there. Okay, so the one of the solution, at least one solution is going to be of this form, where the exponent r may be, it can be either real, it can be complex, or it can be double, it can be real or complex. Okay, which is chosen, this r is chosen in such a way that the first term in this one, a0 is not equal to 0. So I am just choosing this r in such a way that this a0 is not equal to 0. So this ODE has the second solution. The second solution also will be of this form. Okay, the second solutions also will be also such that these two solutions are really different. Maybe similar to it. Maybe of this form with a different r. Okay, here if I have r1, the other one maybe r1 could be there. Or it may contain logarithmic term. Suppose it is having repeated roots or differ by integer or not differ by integer. Depending on that, you will have the logarithmic term also. Okay. So for example, let us see this one. So what I have is I have the let us see like what is going to happen. The initial equation we are going to see. So in this case, what I am going to have, since p of x and p of x are analytic, what I can do is that c of x and p of x are analytic. I can write p of x equal to summation m equal to 0 to infinity bm into x power m. I can write. Similarly, I can write c of x equal to summation m equal to 0 to infinity cm into x power m. I can write. Okay. Now what I got to do, I got to substitute, I am having y of x equal to x power r into am into x power m, etc. is there. Now I am going to find what is the value I am going to get. Okay, so what I am going to find, I am going to calculate y double dash and y dash, etc. is going to be calculated. So y dash is going to become like, so in this case y dash is going to become like, I can write it as this, I can write as summation m equal to 0 to infinity am into x power m plus r, I can write it. Okay. Therefore, y dash of x is going to become like summation m equal to 0 to infinity m plus r into am into x power m plus r minus 1 is going to come. Similarly, y double dash of x is fine. That is going to become like summation m equal to 0 to infinity m plus r into m plus r minus 1 into am into x power m plus r minus 2 is going to come. Okay, so this is the term I have m plus r into am into x power m plus r minus 1 m plus r minus m plus r into m plus r minus 1 x power m plus r minus 2 am is going to be there. Okay, now what I'm going to do is I'm going to collect the least term. Okay, least term means at m equal to 0 whatever the term is going to come. So now what I'm going to do, this one I can write it as, this equation I can rewrite it as x square y double dash plus x into b of x into y dash plus c of x into y equal to 0. Okay, c of x into y equal to 0 I can get. Therefore, if I multiply this by x square into y double dash, this is going to become like m plus r is going to come. X square into y double dash, therefore this is going to become like r minus 2 was that, therefore this is going to become like minus. Now here I have x into y dash, suppose I have x into y dash is going to become like this one. Okay, this term will vanish. Means r minus 1, the x I am multiplying, therefore it is going to become like m plus r is going to come. Now what I am going to do is that I am going to calculate the least term in this one, means m equal to 0. What is the x power r percent I am going to calculate. So in that case I am going to see, I am going to put m equal to 0 and then going to see what is the value is going to come. Okay, if I put m equal to 0, from here I can get, and I got p of x also then. Okay, so here I got p of x also. If I got p of x, okay, so in this case if I got p of x, I am going to collect only the constant term. Okay, the x power r term. So from this one I can multiply. So if I multiply this one, p of x into y dash. Okay, so this is going to become like, I'm going to have some multiplication term is going to come. So if I multiply here I have to, if I want to calculate x power m plus r term, here I have to take the constant term. Here I have to take the x power m plus r plus term. Okay, m equal to 0 term, m equal to 0 only I am going to calculate. Therefore here I am going to take, what I am going to calculate is that I am going to get only p naught is b naught into, here it is going to become like r is going to come into a naught is going to come. Okay, because m equal to 0. So here what I will have, the first term, okay, 0th term only I am calculating. So 0th term, here it is going to become like b naught r into a naught is going to come. B naught into r into a naught is going to come from this one. Now from this one, okay, so I am going to collect for this one the first term only. So from here what I am going to have, I am going to get the m equal to 0 term. Therefore here I am going to get r into r minus 1 into a naught is going to come. Okay, m equal to 0, r into r minus 1 into a naught is going to come. Plus this is going to be from here, and then I have here, okay, here I got to multiply this by c of x. So in that case, c of x is nothing but first term only I am going to take m equal to 0 term. So c naught is going to get, here a naught is going to be. Therefore this is going to become like c naught into a naught equal to 0 is going to. Okay, I am going to collect only the first term from this series. Okay, so therefore what you are going to get, you can write this as a naught out. So what are you going to have, r into r minus 1 into plus b naught into r plus c naught into a naught equal to 0. So you remember that in the beginning of this theorem I mentioned that I have to choose my, in order to find my r, I have to choose my a naught not equal to 0. Therefore since a naught not equal to 0, what I am going to have, I am going to have this equation r into r minus 1 plus b naught into r plus c naught equal to 0 is going to be there. Okay, so this is going to be my initial equation for this problem. Okay, for this ODE, this is my initial equation. So this, from solving this initial equation, so you are going to have, this is a quadratic equation. By solving this one, you are going to get either complex root or real root, and then you have differ by integer or not differ by integer, double root, etc. will be coming. So based on that, you are going to get the two solutions or one solution with log x or etc. is going to come from this one. Okay, so now this theorem 16 Fuchs theorem is what stating the solution of the power series solution when it is going to be applied. Okay, so at least one power series solution will be applied when we are applying this method. Okay, whatever method I have applied, this equations etc. which I applied. So using this method, what you can do is that you can find the at least one power series solution can be applied. Okay, this method of expansion, whatever I have. At the point, ordinary point and singular point. Okay, only for ordinary point and regular singular point only you can find. Not for irregular singular point. Only for ordinary point and regular singular point you can find the solution for this one. Okay, and the number of roots can be determined by this initial equation. From that we will find what is the r1, r2, etc. And using that, you substitute it again in this equation, and find the relations of AM and AM plus 1, etc. Reference relations will come, and then you can expand that and find their common terms. So those things you will see it once you are solving some of the problems in the next class, and also we will see something about the Legendre's equation and Bessel's equations, etc. So with that, I will just conclude today's class. So we'll see rest of things in the next class. Thank you.